Okay, let's start the Aspen Plus tutorial for this week, or I guess problem. So this week we'll try to take a closer look at distillation columns and how to use distillation columns to maybe complement, or I guess distillation modeling tool in Aspen Plus to complement your McCabe-Thiele calculations, which hopefully we're comfortable with now. If you don't know what McCabe-Thiele is, you don't know how to do it, you're having a hard time constructing these diagrams, study your mass transfer or come see me. We can talk about it and give you a quick back of the hand way to do it. But anyways, let's look at this case scenario. And this case is taken from the book by Weinkat. It's one of the commonly used mass transfer books. And so this is the problem taken from the back of the chapter, and these are the pictures, McCabe-Thiele diagrams taken from the solution manual. And the idea here is that we're going to use McCabe-Thiele. We're going to use a combination of both McCabe-Thiele and Aspen Plus to determine a final design of our distillation column for this case. So let's have a look here. So in this case, you're told we have a distillation column with a partial condenser and a total reboiler separating a feed of 200 kilomoles per hour. The feed is 40 mole percent acetone and 60 mole percent ethanol. This writing pad here. The feed is a two-phase mixture that is 80% liquid, and we desire a distillate vapor that's 85 mole percent acetone, and as well as a butts that is 5 mole percent acetone. You're told that the column pressure is 1 atmosphere, and reflux is returned as saturated liquid. Okay, so you're given a lot of information. You're also being told that the L over D of this column is 3.25, and you're told to assume your typical, assume relative volatility and your typical assumptions for when dealing with ideal distillation columns. These are, the common ones are constant relative volatility between the heavy and the light component, and you also assume constant molar overflow as well. It's the second, or another commonly used assumption you make. So you have to find three things. The first thing is find the optimum feed location and the total number of equilibrium stages. What's the minimum external reflux ratio? What's the minimum number of stages? And you need to really differentiate between a couple of parameters when designing distillation columns. The first one is your equilibrium number of stages, and the second one is the minimum number of stages, right? And these are two different ideas, right? Your minimum number of stages is usually less than your equilibrium number of stages. There are different ways to do it. You get your minimum L over D, all the stuff to get these different parameters. And please revise these in mass transfer. Try to know what these mean. And it's just to get a better resolution on what we're going to attempt today. So if I look at the solutions here, so when designing the number of stages or the equilibrium number of stages, we can see that in this case study, we found that the equilibrium number of stages was, you have 5 stages, you have a reboiler at the top, and you have a condenser right here. And so this is your optimum feed location, total number of stages. When looking at the minimum number of stages and the minimum reflux ratio, this is the chart you get where, this is your, these are the parameters you get. You have this number here, and this is your minimum reflux ratio, right? And these are your minimum number of stages, right, at total reflux. And we're going to try to use Aspen to replicate this model. And you have to understand, so let's move to Aspen first before we start talking about what's happening there. So again, I started a new simulation, and as you can see, you show up at the back end, which you basically specify your chemicals, and you need to specify your thermodynamic properties. So for the chemicals in this case, we have acetone and ethanol. So let's go ahead and add these two guys into our simulation right here. So I have simulation 2. I have two components. The first one is acetone, right? Acetone. The second one is ethanol. right? So these are my two components. Again, just make sure when adding components that they show up under component name, you have the correct component name and you have the right chemical formula. If some of these are empty, then you maybe have a typo here. So if I typed ethanol incorrectly, you know, ethanol, whatever, it's not gonna find it and it's gonna give me empty, you know, this table will be empty. So in that case, you can either rewrite it and research for it again, or you can use the find function here to find the chemical you're looking for, okay? Okay, let's wait for Aspen to unfreeze. There we go. So in case you typed it, it's not gonna show up. Just make sure they show up in these two columns to make sure that you have the right chemical. Let's delete this guy from here. Let's go to methods. So after specifying your components, you need to specify your methods. And methods basically your thermodynamic property or your equation of state you're going to use for the species. So let's just use the Peng-Robinson for this method. I'm just going to use Peng-Robinson to show you how to approach this problem. Okay, so I have my Peng-Robinson. Now everything is there. Components are commonly used components. You shouldn't have a problem. Sometimes you might have a problem with the binary interaction parameters. So if you have a red circle next to parameters, just expand it. Expand binary interaction, and to usually be Peng-Robinson K value or the L value. Just click on it. It's going to clear out and retrieve these parameters from a table. But typically you should not get this type of error. But anyways, after we specify these, let's from the bottom left, let's click on simulations to take us to our simulations sheet here, where we're going to start drawing our process and start doing some more, you know, start getting into solving this problem. Okay. So in this case, we're going to look under columns, and under columns for distillation columns, you have a lot of different models you can use, right? You have DSTW, and this uses the Wynne-Underwood method, and the Wynne-Underwood method is a shortcut method which basically tries to replicate McCabe-Thiele, but using equations, using, you know, empirical equations or semi-empirical equations, or I guess they're not empirical, they're more a mass balance type of equation which has been simplified and used. But anyways, you have this shortcut method. The second model is also a shortcut distillation method in Aspen. And the difference between these two models really depends on the type of information you have. Okay, RADFRAC is the most complex type, or that gives you the most details in terms of modeling. And the difference between these two models and this model is that the Wynne-Underwood-Gillian method here and this distillation method, shortcut distillation models, they work backwards. So if you know the feed and you know how much product you want, they can be very helpful in estimating the number of stages, location of the feed stage, etc. Right? However, the RADFRAC works the other way. So the RADFRAC, you know the feed you have, you know the number of equilibrium stages you have, you know the packing you want, so you can use the RADFRAC to try to predict how much, you know, the composition of the products, right? So, you know, they have different uses, and usually when designing a distillation column, at the very initial stage, you want to use a combination of these two. You can use these two to get some back of the hand numbers to try and zone in on your initial numbers, and then once you have these numbers, you take them, you put them in the RADFRAC model to try and get a better resolution of what's happening in this column, try to get a better understanding of the number of stages, what's happening at each stage, etc. Okay. And then you have the extract. This is for, you know, extraction. You know, if you have a stripper or an absorber, you might want to use this model. Multifrac, if you have complex distillation, you have multiple components. Then you have other models which are more complex or more specific to a certain application. So today let's just drop these three models. So I'm gonna drop DST, let's rename it. Rename this DSTWU, and we said this is shortcut model, right? Let's call it SM, shortcut model. Second one is this guy right here, and let's have a look. Let's rename this guy. This is DISTL, and again, this is a shortcut model in Aspen. And then the third guy is RADFRAC, And this is not a shortcut model, it's actually a rate-based model or an equilibrium model. So it has two modes. It can operate as a rate-based or an equilibrium. Equilibrium, it's a more complex type of analysis where it actually calculates the mass balance at every stage, does rigorous calculations at every stage to try and determine what's actually happening in the column. So this is RADFRAC, and this is not a shortcut model, it's just a general model. Okay, let's have a look at the three. So I'm gonna open my blocks here. I'm gonna look first of all at my distillation model just to see the type of input this type of model takes, right? So if you see here in the distillation model, I give it the number of stages, I give it the feed stage, I give it the reflux ratio, condenser type, and some pressure numbers, and then it will be able to calculate what's coming out from the products. But it does a very rough estimate, a very rough mass balance estimate of what's coming from the top, what's coming from the bottom, and this is the type of rough estimate you can do on a piece of paper, and you'll get very close numbers, right? So the amount of insight you get from this, it's not very high, right? So you can use this to verify your McCabe-Thiele calculations. You know, if you get similar numbers, then your McCabe-Thiele calculations are correct, but it won't give you any more insight about what's happening in the column. Okay, let's have a look at the second shortcut method, which is the DSTWU. And if I look at this method, you can see that I can give it either the number of stages or the reflux ratio, and I need to specify the recovery of both the light key and the heavy key component. So if I tell this model, okay, I want an 85% recovery from the top, a 5% recovery from the bottom, with a reflux ratio of 3, please show me what's happening in this column. It will be able to calculate, give you the number of stages, give you the minimum reflux, give you the minimum number of stages, all this stuff, whatever's happening in the distillation column. So you can see these two, depending on the information you have, you can use them to your advantage, right? They're not identical, however, they're designed for the different types of information sets you typically have when looking at distillation columns. Third one is RADFRAC, and as you know, RADFRAC, you can see a lot more details happening here, right? You know, the calculation type, you want equilibrium or rate-based. Rate-based is non-equilibrium. You see now we're looking at transient calculations, more complex design. Unlike equilibrium, McCabe-Thiele is equilibrium. You assume a constant molar overflow, everything is nice and cute. Now we're looking at more details. You need to define your number of stages. For the condenser, we have a lot more options: total, partial condenser. You don't want to operate with a condenser. For the reboiler, again, you can have a kettle, you can have a thermosiphon reboiler as well. Different configurations. You can operate it as a vapor liquid, liquid. So you have a lot more parameters. And when you hear, unlike the other two, we need to specify two parameters when it comes to distillate and reflux, right? And if you have a look here, either you define your reflux rate, reflux ratio, boil up rate, boil up ratio, distillate to feed ratio. You just need to give it two of these parameters so it's able to close the system of equations. It needs more information to be fed into it because it solves a more complex set of equations, so it has a higher number of degrees of freedom. However, it will give you a lot more insight about what's happening really inside the column. So it will tell you at what stage you have weeping, at what stage you have flooding, what's the pressure drop. It can really give you these parameters, which other models can't really give you or won't have a good insight. And in RADFRAC as well, you specify the feed entering your column. If you have multiple feeds, you can specify it using RADFRAC. And you can even have multiple products. You can use the RADFRAC column to have slip streams from the side of the column and recycle them back. You can have, you can really use it to run all types of configurations for your distillation column. And then you specify the pressure at the top, the pressure at the bottom. Alternatively, you can give it a pressure profile. You can tell it, I know the pressure at every stage, and you give it a pressure profile, and it will use these to close the mass balance calculations and the energy balance calculations at every stage. The second important thing about RADFRAC comes to column internals. You can really specify what type of internals you want to use, right? You can say, configurations, or maybe under internals here. You can tell it, okay, I want to add a new set of internals. I want to use a bubble cap tray, between the first stage and the last stage, or maybe I want to have the top part have bubble cap, the bottom part have sieve type of packing, and then it will give you what's happening at every stage. It will give you the liquid holdup, the gas holdup, and any sort of hydrodynamic inconsistencies. It will really show you details of what's going on in every stage. And this is really the advantage of RadFrac is compared to McCabe-Feely, which is your typical calculations compared to using the other two shortcut methods. You can use it to get a higher insight into what's going on inside the column. Okay, so let's go back to our problem. Okay, thank you. Let's go back to our problem. So for our problem, I'm going to use the STW model, right? And let's go back to the prompt here, just to have a look at what we need, or what we're being asked to do. So I have a partial condenser total reboiler, 200 kilomole per hour, 40 mole percent acetone, 60 mole percent ethanol. Phase is a two-phase mixture with 80% liquid. We need a distillate vapor that's 85 mole percent acetone and a bottoms that is 5 mole percent acetone. And the column is at 1 atmosphere. And the reflux is returned as saturated liquid and L over D 3.25. Okay, so let's try to, we have a lot of information. Let's try to slowly feed it into this model right here. So I'm going to drop my stream. So I have my feed stream, I have my top, and I have my bottom streams right here. And let's just rename them. This will be feed. This will be, let's just rename them top and bottom. Top and top. Oh, it doesn't have the name top, doesn't like it, so let's call it vapor, and we'll call this guy liquid, or let's call it bottom. Okay. So I just put in my mass balance. Now let's specify the feed, and we really need to specify just the feed and the conditions of this column. Let's go here. I'm going to open the feed, or you can double click on this guy. Doesn't matter. I'm going to click on input, and I'm going to start specifying what's happening with my feed right here. And again, we don't have the temperature. However, we know the vapor fraction, so I can just set the vapor fraction and the pressure. I know the pressure is 1 atmosphere actually. I know my vapor fraction is 0.2, because in the problem we were told that, wait 1 second, I pause the sharing. Okay, let me share Aspen back again. Okay, so basically I just dropped the 3 streams, the feed stream, the vapor, and the bottoms. I double clicked on the feed or navigated to it from the tree on the left-hand side. I'm gonna start inputting my feed information. And again, we're not given a temperature, we're given a vapor fraction of pressure. So I'm gonna select vapor fraction and pressure. I'm gonna set my pressure to 1 atmosphere and my vapor fraction to 0.2, because in the prompt we're told that the feed is a 2-phase mixture that's 80% liquid. Okay, and 80% liquid means 20% vapor, and then my total flow rate is 200 kilomoles per hour. And then you have acetone and ethanol. So acetone and ethanol, it's 40 mole percent acetone and 60 mole percent ethanol. So I'm going to specify a mole fraction right here, which is 0.4 acetone and 0.6. And you can really use this property where you define the vapor fraction to just set it right here. If you don't want to do it this way, and you want to, for example, you don't want to do it this way, you don't want to specify the vapor fraction here, but you want to find out the enthalpy required to achieve this vapor fraction. Let's say we had a heater here, and you want to use this heater to specify this vapor fraction. So you can do this really by, if I specify the same feed here, or if I just specify ambient conditions in my feed to my heater. So I say, this is going at 25 bars and 1 atmosphere, right? I'm not specifying the vapor fraction because I actually want to calculate the amount of energy required for it to get to this vapor fraction, right? So we said 0.4 here and 0.6. Okay. So and then I have a heater. If I double click on this heater, it will only take the outlet, the temperature required to operate. So you need to determine the temperature that will flash this feed, flashes feed into 20% vapor, 80% liquid. How do you get this temperature? So if you want to approach this problem this way and you want to get this temperature, we need to go back to the properties tab. So I'm going to go back to my properties tab, and so here, just anywhere, just click on binary. So at the top here of your screen, you should see pure binary mixture. We want the binary analysis. So I'm going to click on binary. And we're going to generate a TXY diagram, okay? So just TXY, and you just can keep the default options if you want. You only have 2 species. If you have more than 2 species, you might want to change this. If you have some issues, you can increase the iterations. But let's run this analysis and have a look at our TXY chart, right? And this is how you do it. If you want to use a heater, you know, if let's say you're being told that your feed enters at a certain condition, at let's say at the boiling point or at the saturation temperature, and you want to flash it at another temperature to get 50% liquid, 50% vapor, or you want to heat it, this is how you determine this heat. So you need to determine the temperature at which you want this heater to operate. And to determine this temperature, we need to look at the TXY plot, which is what we have here. So here I have my TXY plot. This is my temperature. This is the you know, mole fraction of acetone. And in order to determine the temperature at which I'm going to operate, or at which I'm going to get 20% vapor, 80% liquid, you need to know the feed, the Z, you know, the Z composition or the feed composition, whatever it is. And so in our case, our feed is it 40 or 60? It's 40 mole percent acetone. So this would be the line I'm looking at. You see this 40.4 line, and this is my feed line right here. And I need to find the point in this envelope. I need to find the point along this line where the distance here, so the distance on the left-hand side represents the vapor, and the distance on the right-hand side represents the liquid. I need to find the distance where basically it's 20% vapor and 80% liquid, right? So the distance from the 0.4 line to the blue curve should be a quarter of the distance between the 0.4 line and the green curve. And I think you've done this in mass transfer by this point in the course. So if I look here, let's look at this point. It's a nice cute point, the intersection. Here I have about 2 3/4 blocks. And here I have 1, 2, 3, 4, 4. So 2 and 4, it's not exactly what I'm looking for. Let's go down a bit here. Here I have about, maybe here about 1.5. And here I have 1, 2, 3, 4, 5, 6. So 1.5 to 6, that's a 1 to 4 ratio. So maybe, so this is the temperature really, which will give me the separation. Somewhere here, it's not exactly halfway through, it's maybe a bit above it. So maybe 67 and a quarter or 67 and a half would be a good estimate. And this will be the temperature that will give me a split of 20% vapor and 80% liquid. So once you have this temperature, you go back to your simulation. And, okay, this guy froze now, give it a second. Go back to the simulation, let's go. And you click on your heater and you're gonna run this heater at this temperature. So if I run my heater at, we said 67 and a quarter, 0.25, and we said the pressure was 1 bar. Is it 1 bar? Let's skip, no, we want the pressure to be 0. So you have no pressure drop. If you set this parameter 0, it's not gonna change the pressure. So I'm gonna set it to 0. Then I'm just gonna run it to show it. So I'm gonna deactivate these guys here. And then I'm gonna run the simulation just just to get some results for here. So if you run B4, it's not happy with this. Okay, we will have a look at it once after we run this guy as well. But anyways, S5 should be 20%. Rename it 2080 vapor liquid. It will be around 20% vapor, 80% liquid. Anyways, so let's go back to our original original column. So here I just specified my vapor fraction to be 0.2. You can fix the feed. It's not going to give you a lot of energetics, not going to give you a lot of information about how you get to this point, but it will just assume it's at this point. Or it's just going to force it, it will be that it's at this point. So of course, it's going to calculate your enthalpy, your heat capacities, all these parameters. Anyways, let's go back to our shortcut column. Let's have a look at the parameters for this column. And one thing to remember about using these shortcut columns, they're never going to converge for you, okay? Every time you run them, you're going to get an error unless you're running a very well-defined case and you know all the parameters in advance, then maybe you won't get an error, but should be comfortable that when you run these shortcut methods, most of the time you're going to get an error. However, it will still give you some results, and the results you get is what's really useful. Okay, number of stages, we don't know the number of stages, however, we know the reflux ratio was given to be 3.25. And one thing when defining the reflux ratio, if you know the reflux ratio as is, you specify it. If you're told that the reflux ratio is a multiple of your minimum reflux ratio, so for example, if I told you I'm running this column at reflux ratio that's 1.5 times the minimum reflux ratio, in that case, you don't enter a positive number, you're going to enter a negative number. So if I tell you the reflux ratio is 1.5 times the minimum reflux ratio or 2 times the minimum reflux ratio, you need to add this minus sign here. If you're just told the reflux ratio and L over D value directly, then you just enter it as a positive number. Okay. And then we're going to specify our components. So what's our light component? What's our heavy component? So from our problem, we're being told that, back to the vapor is 85 mole percent acetone. So I have acetone here at the top and I have ethanol at the bottom. And you're being asked for the recovery, okay? Recovery is not the fraction, is not the amount, is not the composition of your product stream. Let's just go back and let me share my whiteboard. Let's have a look at this definition of recovery here. So in this case, I have a feed, right? Entering, let's try to do this properly. Entering a distillation column, so it's just a box, right? And from the top, I have a stream. From the bottom, I have a stream. You're being told that the feed is 200 kilomole per hour, and it's 0.6 acetone, 0.4 ethanol. You're also being told that this stream here has a composition of 0.85 acetone. And let's call the flow rate of the stream, let's call it F top. And here has a 0.05 acetone, and let's call this flow rate F bottom. Okay, so this composition is not my recovery. My recovery is actually how much the number of moles of acetone here compared to the number of moles of acetone in the feed. This is my actual recovery. So let's do a mass balance. Let's find out how many moles of number of moles of acetone we have in the feed. So this will be 200 by 0.6. This is 120, and number of moles of ethanol is 200 by 0.4. This is 80, right? These are number of moles. I don't know F top, I don't know F bottom. However, I know F bottom is 200 minus F top. So I have enough information to build a mass balance. So my mass balance will be, if I build a mass balance for acetone, 200 times 0.6, 0.85 to F top is equal to, is equal to This has to be plus. Let's undo this guy. Plus 0.05 into 200 minus. This is the mass balance for acetone, which number of moles of acetone going in is equal to the number of moles of acetone at the top, which is 0.85 composition multiplied by the flow rate, plus number of moles of acetone on the bottom, which is 0.05 composition multiplied by the flow rate, which is F bottom. However, F bottom is 200 minus F top. If you solve this equation, you should get F top to be 137.5. And from here, you can deduce that F bottom is equal to, let's calculate this number, it's 200 minus 137.5, which is 62.5. So now I know the flow rates at the top, I know the flow rates at the bottom. I can calculate, or I can determine my recoveries at the top and at the bottom as well. Okay, let's determine these numbers. So F top here will be 137.5. So number of moles of acetone in this top stream will be 0.85 multiplied by 137.5. And this is 116.875. And ethanol will be just minus 137.5. This will be 20.625. And then from the F bottom, I can also get the number of acetone, and this, of course, these are in the top, and these are in the bottom, or and acetone in the bottom stream will be 0.05 multiplied by F bottom, which is 62.5. So I have 0.05 multiplied by 62.5, and this number is 3.125, and ethanol in this case will be just the difference, 62.5 minus 3.125, and this guy will be 59.37. So from these, I have a full resolution of this column now. I can get my recovery for acetone and ethanol, right? So recovery of acetone in the top will be the number of moles, which is this number, divided by the number of moles acetone in the top feed, divided by the number of moles of acetone in the feed, right? Number of moles of acetone in the product, top product, divided by number of moles of acetone in the feed, which is 116.875 divided by 120, and this number right here will be 0.9774, and the recovery of ethanol in the bottom in this case will be how much ethanol we have, 59.375 divided by the original number of moles of ethanol entering this column. So this will be 59.375 divided by 80, and this number will be 0.742, right? So now I have my recovery at the top, recovery of acetone from in the top stream, and recovery of ethanol in the bottom stream. Let me write these numbers down. So these numbers are 0.974 and 0.742. Okay, let's go back to our Aspen Plus simulation, and let's see how we're gonna use these numbers to model this column. But again, Aspen is not a black box. You need to use Aspen to supplement what you're doing, to supplement your calculations, supplement your engineering judgment, right? All right, so we said acetone, the recovery at the top is 0.974. You should never use Aspen as a black box. Garbage in, garbage out. You have no clothes garbage. It's shambles. Okay, anyways, ethanol recovery at the bottom is 0.742. So now I have my recoveries at the top and at the bottom. Good. So now what are we missing? We're missing the pressure at the condenser. So it's total condenser, which is as given in the problem, we just specified here. If it's partial condenser, you can specify it as well. However, if it's a total condenser, I'm going to set my, it's total condenser and the pressure in the column does not change. I'm going to set my pressure as the feed pressure, which is 1 atmosphere at the top. and 1 atmosphere at the bottom. Okay, here we go. So I have my numbers here, and here I have everything needed to solve this problem. I highly recommend that after doing this, I highly recommend that you basically just increase your conversions, because Aspen tends to have issues when dealing with distillation column conversions, or when converging distillation columns. So just increase your number of maximum iterations a bit, just to make sure, you don't run it, or, if Aspen gives you a severe error, which is, Aspen will probably give us a severe error, it's going to give us an error, you at least get as close as possible to the number before it exits the calculations. Okay, so now we have everything set up. I'm going to run the simulation right here. And when running these back of the hand models in Aspen, just be comfortable with getting errors, right? It's going to happen. Very rarely does it converge. If you want it to converge, you need to really take these numbers and really feed them into Aspen again and do this a bunch of times. But because it's a back of the hand simple model, it's not worth it, right? Just take these numbers and use a more sophisticated model to get your final design. Okay, let's wait for Aspen to give us some numbers here. Okay, Aspen will tell you, some results are present, but wasn't able to do much. It's fine. And you're gonna get some errors, right? Component flows, minimum reflux ratios does not match. This is a very common error. That's fine, it's not a big deal. So what you need to do is navigate to results and look at the summary, right? So here at the summary, we have a lot of very useful information for your design. Specifically, your actual reflux ratio, minimum number of stages 3.15, actual number of stages 3.6, your optimum feed location 1.6, number of stages above the feed, your boiler heating required. I'm going to convert these to megawatts. Right? You can use kilowatts, but just be careful with your units and calories per second. I don't like this unit. Let's make it megawatts here. Megawatts as well. So you can get your reboiler duty, your condenser duty, your distillate temperature. You can have a lot of useful information, which you can use now to make a more sophisticated design of the column. And if we compare these results to the results we have from the solution manual for this problem, specifically my minimum number of stages, which is 3.15, and my actual number of stages, which is 3.6, and as well as my feed stage, which is 1.6. If I compare these to the problem right here. So if I have a look here, we said the minimum number of stages we have was 3.6. If I look at the solution to this problem, when using the McCabe-Feely, they have 1, 2, 3, 4. They actually have 4 as the minimum number of stages. This is your condenser right here, right? So don't worry about this guy. This is your reboiler right here. But anyways, we have 4 stages here. Aspen told us 3.6. Optimum feed location was 1.6 when using Aspen. When using this graphical method, it's about 2.5, or it's a bit over 2. So the numbers are close, and you can definitely use either of these methods, either of these numbers to either verify each other. You want to double check your work. They're not going to be identical because the Underwood equation will not give you the same number as the McCabe-Feely method, and how what tool you're using to McCabe-Feely will change from different person to person. Some people are very neat, so they can get these lines, perfect slopes and everything. Some people, just 1 degree in the line, and you're off by 2-3 stages, which is not a big deal at the very initial design when we're designing a process. However, as you close in on your distillation column, it starts to make a big difference in your metrics. But anyways, so we have our actual number of stages and we have our minimum number of stages, and we're going to use these numbers to have a better look at the distillation column. So let's take these numbers and let's start. Let's take these numbers and let's try to get a more sophisticated simulation of this column using a RAD-FRAC model. So I'm going to go here, I'm going to do separators, no, not separators, columns. I'm going to use a red frac model right here. And let's rename this block red frac model. Yeah, let's call it red frac 1. It doesn't like the 1, it's fine. Let's call it red frac. And I'm going to just model this in first. One thing before moving on is we talked about how we're going to use the heater to change its vapor fraction by looking at the temperature at the TXY diagram. So if I look at the output of this heater, it should be 20% vapor, 80% liquid, if we read the chart properly, right? If we weren't able to read the chart, or we weren't able to gauge it visually very well, then we're going to get a different number. But let's have a look here and let's verify what we did. Okay, let's have a look. So if you look at the results of the stream, you can see that liquid fraction is 0.8, vapor fraction is 0.198. So we're able to get the distribution we wanted. And again, in order to do this, if you don't want to specify it in the feed directly, and you want to use a heater to get this temperature, and the advantage of using the heater is to give you some information about the enthalpy required to reach this condition. And this information can be useful when maybe you want to get a better sizing of your plant, or you want to get a higher resolution of the process. Then this will be good. And the way we did it is we went to our simulation Aspen. We did a binary analysis. So again, click on binary at the top here. So make sure you have the right metric selected. If this is flipped, looking the other way, just go back and select the other component, right? So if I draw this in terms of ethanol, this envelope will look this way, right? So look the other there, point the other direction. It's fine, doesn't matter. But if it really bothers you and you want to always have it looking this way, then just change the component. It's going to flip. We determine our feed composition, which is 0.4. If you have a 50-50 feed, look at 50.5, or in our case 0.4, you go up the line, and then you find the point along the line within this envelope at which the vapor amount is 25% of the liquid amount, right? Or vapor over liquid is 20, or vapor over the entire line is 20%, right? So I just find the point along this line. And again, you just by gauging the distance here and the distance here and comparing them to each other and comparing them to the overall distance, right? Once you find the temperature you want, this will be the temperature that will give you this vapor liquid split. And you just set it in your heater, and then you also have some metrics for the heater. So if you go back to the simulation as well, and I look at my heater here, so back to our flow sheet, I double click on my heater. If I look at results, I'm gonna get some results for that metric, for these steps of how much enthalpy or how much heat duty does this heater need, right? So you can say, okay, so in this process, I need to pump 0.68 megawatts to flash it to 2080, right? And this is an important parameter for you when designing a column. Usually you want to have this degree of resolution. But anyways, so after getting the numbers from the DSTW, we can always use a red frac model to try and get a better or a higher understanding of what's happening in our column. And so if I click on S1, I'm gonna try to model the same thing using a red frac model. And next week, we'll talk in more details about red frac. And then last week, I'll keep it for reactors. And next semester, we'll also do Aspen as well. So that hopefully you can, I know access is not very easy now remotely, but over a year, hopefully, you see it a lot more often, you get more familiar with it. So the mole is just a given from the mainstream. So the Aspen is 0.4, 0.4, this mole fraction, right? 0.4. This guy right here is 0.6. And I have my feed into this red frac model. Let me close all of these tabs right here. Go to the main flow sheet. Now I'm going to specify what's happening in my red frac. And I'm going to use the results I got from my other column to try and model this red frac. So we said we have 4 stages, so I have 6 stages overall, 4 reboiler condenser. We said our condenser is a total condenser. Sorry, it's is that total? Is that partial? Partial condenser. And the error Aspen gave me here when I set a total condenser was that it will tell you consistency error in the value settings, phase vapor, total vapor is not allowed for distillate stream when condenser equals total condenser. And what this means is if you took a closer look when we were connecting our material stream here, so for red frac, let me delete this guy. Can we connect? Okay, for red frac, when you're connecting a material stream, you have 2 options. You have this option right here, the bottom arrow, which is liquid distillate. And this is required if you have a total condenser. If you have a total condenser, you only have a liquid from the top, right? So everything's being condensed. However, if you have a partial condenser, you're going to have some vapor product, and then the liquid product is typically sent back as reflux back into the column. Okay, so again, we have a partial condenser. So I connected it to the vapor partial condenser. Your reboiler, you can, so usually kettle is the easiest one to converge, or if you want, you can set thermosiphon, it's a bit more advanced, or none. So we have our reflux ratio, so I'm going to set my reflux ratio here at 3.25. And one thing you need to remember is you see reflux ratios here, but it's not showing up in this list. That's because it's already been selected here, right? So if I select distillate rate here, distillate rate is not going to show up in this list. Okay, it doesn't mean, it's just you know, don't get confused by this simple thing. And then we need to enter a second piece of information. We don't have any information other than the reflux ratio. However, from modeling our simple model, or what did we call a shortcut model, we have some information about the energetics, right? We're going to use this to feed it into our red frac model. Specifically, I have my reboiler heating or my condenser cooling. Let's use the reboiler heating requirement. And this will be 6.48 megawatts. I'm going to feed this into my red frac. So here I'm going to use my, let's see, reboiler duty. And I'm going to put 6.5. Let's put a 6.5. And we said it's megawatts, right? This will be my reboiler duty. Okay, so I put in as much information as I have. And I'm going to go to streams. And we said the feed stream is at 1.6. So let's say, let's put it at stage 3. That's fine. I'm going to put it at, always put it at stage or above stage or on stage. These differences, these are very subtle differences. However, if you study your, you know, once you get more comfortable with distillation columns and taking a closer look at the book and all of these details, you should be able to get a better understanding, or you know, have a better feel of these differences. I'm not sure with my mouse here today. Let me try to do this properly. So I want to have this on stage. Here we go. And then for the pressure, I'm going to keep the pressure fixed throughout the column. Sometimes if you have a high pressure column, or you know, if you're operating, or if your feed is coming in at 10 bars, you want to use the pressure to your advantage, because it's a thermodynamic manipulation as well. However, our feed is coming in at atmospheric pressure, so we don't need to worry about this. And again, I'm going to make this atmosphere, and that should be enough, right? You just need to specify one stage. You can specify a profile if you want. You can do all types of things. And then these are some more advanced models for modeling condenser and reboiler. You can specify a subcooled temperature. You can specify the shape of the reboiler you're using. sorry, you can have, if you select the thermosiphon or boiler, you have different configurations which you can select. But anyways, so after specifying all of this, I can run my simulation this way, and this is usually the point of using RadFrac, I can specify my column internals. And this is a very important feature to do this. And this is what I'm going to do. I'm going to specify my column. And this can give you some understanding of what's really happening inside this column. What's going on here. Click on this. It's going to take you to a new sheet where we're going to specify, take a closer look at the internals. Okay, let's wait for it to load. There we go. And you get this table which you're specifying internals, and I'm going to add a new section, right? And this section will be stages 2 and 5, right? Because we have 60, we have 4, we have one at the top, one at the bottom, 6 overall, and then the middle guys are 4. So I'm going to pack all the middle stages starting at stage 2, ending at stage 5. I'm going to pack this entire area. I'm going to have it trade, and let's use bubble cap. You can use any, you can use any type of packing you want, right? A lot of different things. You can even use packed internals. You have brushing rings, you have saddle, pearl saddle, all types of things happening inside your column. And then you can also specify your column height, 0.6096 meter. I think this is 2 foot, right? But you can specify any you can specify you can specify the height, you can specify the diameter as well. So you can play around with these parameters until you're comfortable. Okay. Anyways, so you specify your packing, and then this can give you can view hydraulic plots. It will give you more details about what's happening in each tray, in terms of weeping, in terms of pressure drop. You can see exactly what's going on, liquid mass flow rate. Where should you operate? Where's your weeping point? All this stuff. But anyways, we're gonna talk about this in details next week. So for now, let's just run this simulation and see some results. And it's typical when using these distillation columns, you're gonna get errors. Aspen is usually not happy, but that's fine. You can iterate, you can always solve. However, in our case, it was fine, and we were able to get some results. We were able to see what's happening inside the column. So when you run your RadFrac, you see your results here. You have profiles. You can use this profiles tab to give you a good understanding of what's happening at each stage. So I can see at each stage, I can know my number of moles of liquid, my number of moles of vapor. You can change the units. You can see exactly what's going on in every stage, right? And then you can see your overall stream results, of course, which will give you the overall mass balance, overall energy balance of your process. But usually use this to use RadFrac. The insight RadFrac gives you is in the profiles, right? Where you really see what's happening at every, and these are mass balance results. They'll match or be very identical to what we did using the Cape Feely or back of the hand calculations, all this stuff. However, it really results is really where you see profiles really where you see your insight. You can also see the compositions at every stage. At every stage I can see my compositions here. You can make plots if you want. If you want to plot the composition of these guys, you can always do that using these features at the top. And the other thing you can see is your hydraulic plots from Aspen or from the RadFrac model, where you can see at every stage. I can see what's happening. Which stages are okay, which stages are not running very well. So here you can see it's telling you stage 2, you have to be careful with stage 2, maybe take a closer look. Stage 5 is fine, but we have some warnings. And we also see the column hydrodynamic results here as well, where it gives you some more details about hydrodynamics, okay? So this is really how you use these two models, your back of the hand shortcut models, which we said are DSTW and distillation, and then more detailed distillation column model, which is the RATFRAC, how you can use them together, how you can use them to complement your McCabe-Thiele, to complement each other to try and get a closer or a better resolution of this distillation column. And we also discussed how to, if you don't want to flash it in the feed itself, you can always use a heater to partially flash it, and how to get the temperature from your property step. Okay, so please try to replicate this. What I want you to do for this tutorial is to replicate the results from the DSTW model. However, use 3 different equations of state: Raoult's law, Wilson's equation, and RTL equation. Change the equation of state, run the DSTW model, get the number of stages, equilibrium number of stages, all these heat parameters, and compare the results using these 3 equations of states. Put them in a nice table, and these will be the results. This is not a group homework, this is an individual homework. So each one of you should submit it individually. Okay, next week we'll talk in more details about RATFRAC, how to play around with RATFRAC, how to have turnarounds, bypasses from a distillation column, all of these different scenarios. Thank you very much, and I'll talk to you guys next week.